If you stepped outside tomorrow morning and found two brilliant stars rising together in the eastern sky, casting overlapping shadows at your feet, your life and every life on Earth would change forever? The familiar rhythm of day and night, the gentle cycle of seasons, the very foundation of how energy flows through our world would shift into something both beautiful. An alien. Picture this moment, standing in your garden as twin suns climb the horizon, their combined light painting the sky in hues no human has ever witnessed. One sun, perhaps slightly smaller and more orange than our familiar yellow star, dancing eternally with its larger companion. This isn't science fiction. Binary star systems make up more than half of all stellar populations in our solar neighborhood, and recent discoveries by NASA's Kepler Space Telescope have revealed planets orbiting to stars and systems like Kepler 47, worlds where double sunrises and sunsets occur every single day. Tonight, as we drift through this cosmic thought experiment together, we'll explore what it would truly mean for Earth to exist in such a system. We'll discover how binary star systems form, why they're far more common than our solitary sun, and what life might look like under the gentle glow of two stellar companions. From the strange seasons that would emerge to the completely different evolution of life itself, we'll paint a picture of an Earth both familiar and wondrously transformed. But that's only the beginning. The real magic happens when we consider how this double star dance would reshape not just our days, but our nights, our weather, and perhaps even the emergence of consciousness itself. If you stepped outside tomorrow morning and found two brilliant stars rising together in the eastern sky, casting overlapping shadows at your feet, your life and every life on Earth would change forever. The familiar rhythm of day and night, the gentle cycle of seasons, the very foundation of how energy flows through our world would shift into something both beautiful and alien. Picture this moment with me. You're standing in your garden as dawn approaches, but something feels different even before you see it. The horizon glows with an unusual warmth, a soft amber light that seems to shimmer with complexity. Then they rise, two suns, one perhaps slightly smaller and more orange than our familiar yellow star, dancing eternally with its larger companion. Their combined light paints the morning sky in hues no human has ever witnessed. Deep golds blending into warm coppers, with shadows that shift and dance as the twin stars climb their celestial path. This isn't the realm of pure imagination. NASA's Kepler Space Telescope has revealed multiple planets orbiting binary star systems, including Kepler 47, where worlds experience double sunrises and sunsets every single day. Binary star systems are actually the most common type of stellar configuration in our galaxy, making our solitary sun something of an oddity in the cosmic neighborhood. In fact, more than half of all stars in the Milky Way exist as part of multiple star systems, locked in gravitational embraces that have lasted for billions of years. As you watch this hypothetical double sunrise, notice how the light feels different on your skin. Instead of the single, steady warmth of our sun, there's a gentle pulsing quality to the heat, sometimes warmer as both stars align their energy toward you. sometimes cooler as one pauses behind the other. The shadows at your feet tell a story of cosmic complexity, two distinct dark shapes that merge and separate throughout the day, creating patterns of light and shadow that would be impossible in our single-sun world. Scientists at the Harvard-Smithsonian Center for Astrophysics have studied how planets in binary systems experience dramatically different seasons and climate patterns compared to our Earth. In our imagined two-sun Earth, you might witness a morning where one sun rises first, casting long shadows across frost-covered grass, only to have the second sun appear an hour later, quickly melting that frost into gentle steam that rises like morning prayers toward the brightening sky. But let's pause here and truly absorb what we're imagining. You're not just observing a different sunrise. You're witnessing the result of a completely different stellar birth story. Recent research suggests that our own sun may have once had a binary companion, a stellar sibling that was lost to the gravitational tides of our galaxy's formation. If that companion had remained, if Earth had formed in that binary system, this morning's double dawn would be as natural to you as breathing. Consider the sounds of this world. Birds would sing different dawn choruses, their internal clocks adapted to the complex rhythms of dual stars. Perhaps some species would greet the first sun with soft, low calls, saving their most elaborate songs for the moment when both suns share the sky. The very air might feel different, not just warmer or cooler, but somehow richer, as if charged with the energy of two stellar hearts beating in cosmic synchrony. The habitable zone around binary star systems is far more complex than around single stars, creating regions where liquid water can exist despite the varying stellar radiation. In our two-sun Earth, you might find deserts that bloom only when both stars align just right, creating brief seasons of extraordinary fertility, or mountain regions that experience two distinct growing seasons per year as different peaks catch the light of different stellar companions at different times. As the morning progresses and both suns climb higher, you begin to understand that time itself would feel different here. The concept of noon becomes beautifully complex. Is it when the first sun reaches its zenith? When the second does? Or perhaps when both stars achieve perfect balance in the sky, creating a moment of such brilliant illumination that the whole world seems to pulse with golden fire on the real planet Kepler 47b. These questions aren't hypothetical. This world, roughly the size of Neptune, experiences exactly this kind of stellar complexity every day. While it's too large and gaseous for human life, it proves that our imagination of a two-sun Earth isn't fantasy. It's a real possibility that exists elsewhere in our galaxy. Children born into this world would grow up with a completely different relationship to light and shadow. They would learn to tell time not by the position of a single sun, but by the intricate dance of two stellar companions. Their games would involve the complex patterns of dual shadows. Their art would capture colors that exist nowhere in our single-sun world. Their mythology would be rich with stories of the stellar siblings who bring light to the world, tales of when the stars embrace and when they dance apart. As this first imagined day with two suns continues, you realize that everything, from the way plants grow to the migration patterns of birds, from the formation of weather systems to the rhythm of your own sleep, would be fundamentally different. The earth beneath your feet would still be home, but it would be a home transformed by the gentle tyranny of dual starlight. But that's only the beginning of our journey together. The real magic happens when we step back even further, beyond this single morning, beyond this transformed earth, to understand where such stellar partnerships are born in the first place. We must venture into the stellar nurseries of space itself, where gravity and gas and cosmic chance come together to create not one sun, but two, locked in a gravitational embrace that can last longer than planets themselves. To understand how our Earth might have come to dance with two suns, we must journey backward through deep time, to the stellar nurseries where binary companions are born. Picture, if you will, a vast molecular cloud drifting through the spiral arms of our galaxy, a ghostly cathedral of gas and dust stretching across dozens of light years, so thin that it barely whispers against the vacuum of space, yet so massive that within its gossamer walls lie the seeds of thousands of future stars. These stellar nurseries are among the most beautiful and mysterious places in the universe. Recent observations from the ALMA telescope array have revealed that 60% of these molecular clouds possess an intricate filamentary structure, delicate threads of matter weaving through space like cosmic silk, while the remaining 40% maintain what astronomers poetically describe as fluffy architectures, resembling celestial cotton floating in the cosmic wind. Within these enormous structures, gravity begins its patient work. Over millions of years, the lightest touch of gravitational attraction draws particles together. A grain of dust attracts another. Hydrogen molecules drift toward slightly denser regions. What begins as the gentlest of cosmic breezes gradually becomes an irresistible tide. And within this tide, the story of twin stars begins to unfold. Scientists at the University of Massachusetts have discovered that binary star formation follows two distinct pathways, each as elegant as it is complex. The first, called turbulent fragmentation, occurs when the natural chaos within a stellar nursery becomes too much for a single collapsing core to bear. Imagine a slowly rotating cloud of gas beginning to contract under its own gravity. As it shrinks, turbulent eddies and swirls develop within the cloud. Cosmic weather patterns that grow increasingly violent as the density rises at a critical moment. This turbulence becomes so intense that the cloud literally tears itself apart, fragmenting into multiple dense clumps. Each clump continues its gravitational collapse independently, eventually igniting nuclear fusion and becoming a star. The fascinating detail, revealed through sophisticated computer simulations, is that these separately formed stars retain no memory of each other's rotational history. When we observe their protostellar outflows, the magnificent jets of matter they launch into space during their birth, we find them pointing in completely random directions. Like cosmic lighthouse beams swept by independent hands. The second pathway, disk fragmentation, tells a more coordinated story. Here, a massive accretion disk forms around a single collapsing core. a spinning pancake of gas and dust that can stretch for hundreds of astronomical units. Within this disk, gravitational instabilities begin to develop, creating spiral patterns that grow more pronounced over time. Eventually, these instabilities become so severe that a secondary disk forms within the first, like a smaller wheel spinning inside a larger one. This secondary structure accumulates enough mass to collapse into a second star, creating a binary system where both companions share a common rotational heritage. The evidence for this coordinated formation appears in the alignment of their protostellar jets, unlike the random orientations seen in turbulent fragmentation. Disk fragmentation produces binary stars whose jets point in similar directions, betraying their shared angular momentum history. It's as if the cosmos has left us a signature, written in streams of superheated gas launched across interstellar space. But the story becomes even more intriguing when we consider the research conducted at Northwestern University, which has revealed how newborn stars can dramatically reshape their birth environments. These wandering stellar infants, still glowing with the heat of formation, move through their molecular cloud nurseries like cosmic storms, their powerful magnetic fields and stellar winds disrupting the delicate structures around them. They twist and tangle the magnetic field lines that thread through the cloud, creating turbulence that can trigger the formation of additional stars or prevent it entirely. This discovery suggests that star formation is far more dynamic and interconnected than previously imagined. The birth of one star influences the birth of others, creating complex feedback loops that ripple across entire stellar nurseries. In our hypothetical two-sun system, we might imagine that the formation of our first stellar companion triggered exactly the right conditions for the second to follow, like cosmic dominoes falling in a sequence that spans millions of years. Recent observations from the Very Large Ray Radio Observatory have detected binary companions forming around protostars that are less than 100,000 years old, stellar newborns by astronomical standards. This means that the gravitational dance between twin stars begins almost immediately after their birth, when they are still surrounded by the dusty cocoons from which they emerged. The timescales involved in these processes humble our human perception of permanence. What we witness as this stable dance of binary companions represents the end result of gravitational processes that unfold over millions of years. The molecular cloud that gave birth to our hypothetical twin suns would have begun its collapse when our galaxy was measurably different than it is today, when spiral arms occupied different positions, and different populations of stars illuminated the cosmic neighborhood. Yet for all their vast scales and ancient origins, these stellar births follow surprisingly predictable patterns. The Harvard-Smithsonian Center for Astrophysics has catalogued thousands of binary systems, revealing statistical regularities in their properties. Most binary companions form with orbital periods ranging from a few days to thousands of years. The mass ratios between partners follow specific distributions that reflect the physics of fragmentation and accretion. Perhaps most remarkably, studies of the Masses Survey, a comprehensive examination of binary protostars, have confirmed that the alignment patterns predicted by turbulent fragmentation theory match what we observe in nature. The random orientations of protostellar jets in young binary systems provide compelling evidence that turbulence, rather than orderly disk fragmentation, dominates the formation of stellar pairs in our galaxy dot as we contemplate our Earth orbiting twin suns. We're not just imagining an arbitrary cosmic arrangement. We're envisioning the end result of one of the universe's most fundamental processes, the transformation of diffuse interstellar matter into concentrated stellar furnaces through the patient, inexorable action of gravity and the chaotic beauty of turbulence. But now that our twin stars have been born from their cosmic cradle, igniting their nuclear hearts and settling into their gravitational embrace, a new chapter begins. For if Earth is to exist in this system, it too must find its place in this stellar dance, carving out an orbital path that can remain stable across billions of years. Now that our twin stars have ignited their nuclear hearts and settled into their gravitational embrace, we must consider perhaps the most delicate question of all. Where, in this complex stellar waltz, could Earth find a stable home? The answer leads us into one of the most beautiful and challenging problems in celestial mechanics, a cosmic choreography so intricate that it has fascinated mathematicians and astronomers for centuries. Imagine standing on the edge of our solar system, looking back toward the center where our twin suns orbit each other. From this vantage point, you would witness what astronomers call the three-body problem, a gravitational puzzle that involves the intricate dance between two stars and our planet. Unlike the simple elegance of Earth's current orbit around a single sun, which follows predictable elliptical paths described by Kepler's laws, the motion of a planet in a binary system creates patterns of such complexity that no mathematical equation can fully solve them. The Institute for Advanced Study describes the three-body problem as the oldest unsolved problem in mathematical physics. When three celestial bodies orbit each other under their mutual gravitational influences, the resulting system becomes chaotic for most initial conditions. Unlike the two-body problem, which has a clean, closed-form solution, the three-body problem requires us to use numerical simulations to trace the endless dance of gravitational forces, pulling our planet in multiple directions simultaneously. Yet nature has found ways to make this cosmic choreography work. NASA's Kepler Space Telescope has revealed 17 confirmed circumbinary planets, worlds, that have successfully found stable orbits around binary star systems. These discoveries prove that our imagined Sun-Earth is not merely possible, but represents a planetary arrangement that already exists elsewhere in our galaxy. The key to understanding how Earth might orbit twin suns lies in recognizing that there are two fundamentally different types of stable orbits in binary systems. The first, called an S-type or circumstellar orbit, would place our planet in orbit around just one of the two stars, while the companion star orbits at a much greater distance. In this arrangement, one sun would dominate our sky while the second would appear as an extremely bright star, rising and setting with the seasons. But far more intriguing is the second possibility, a P-type or circumbinary orbit, where Earth would orbit both stars together, treating the binary pair as a single gravitational unit. This is the arrangement that would truly give us two suns sharing our sky. rising and setting in their eternal dance, while our planet traces a vast ellipse around their combined mass. Recent research has revealed that stable circumbinary orbits exist only beyond what astronomers call the critical radius, a minimum distance from the binary pair, where gravitational perturbations don't tear a planet's orbit apart. This critical distance is roughly 2 times the separation between the binary stars themselves. Remarkably, observations of Kepler's circumbinary planets show that they orbit remarkably close to this stability boundary, with semi-major axes between 1.09 and 1.46 times this critical radius. The reason these planets cluster so close to the stability limit tells a fascinating story of planetary migration. Computer simulations suggest that these worlds likely formed much farther out, beyond what astronomers call the snow line, where temperatures were cold enough for ice to form. Over millions of years, they migrated inward through gravitational interactions with their birth disks until they reached the edge of the dynamically unstable region. There, the complex gravitational forces from the binary stars would have halted their inward journey, leaving them in the orbits we observe today for our hypothetical to Sun-Earth. This migration history would mean a dramatically different geological past if Earth formed beyond the snow line of a binary system. It would have begun its existence as a frozen, ice-covered world. The gradual migration inward would have been accompanied by a slow warming as our planet drifted closer to its dual stellar sources of heat. The early atmosphere, the formation of oceans, the emergence of geological activity, all would have occurred during this grand migration, creating a planetary history unlike anything we see in our single-sun solar system. The orbital mechanics of our circumbinary Earth would create patterns of motion that challenge our terrestrial understanding of seasons and years. The planet's distance from the binary center would vary not just due to its own elliptical orbit, but also due to the orbital motion of the binary stars themselves. When both stars align on the same side of their orbit relative to Earth, our planet would receive maximum heating. When the stars are positioned on opposite sides of their binary orbit, the heating would be more distributed and potentially less intense. These variations would occur on multiple timescales simultaneously. Earth's own orbital period around the binary might last several hundred of our current Earth days, while the orbital period of the binary stars around each other could range from a few days to many months. The complex interaction between these different periods would create what astronomers call beat frequencies, long-term cycles where the heating patterns repeat only after many orbital periods of each component. Recent studies of Kepler 47c, a gas giant orbiting in the habitable zone of a binary system, have shown how such worlds maintain stable climates despite these complex heating patterns. The gravitational influence of the binary creates what researchers describe as a self-regulating effect, where orbital variations tend to average out over time rather than leading to runaway heating or cooling. But perhaps the most remarkable aspect of our circumbinary Earth would be the view from the surface. Unlike our current world, where the sun's position in the sky follows predictable daily and seasonal patterns, the motion of twin suns would create an ever-changing celestial display. Some days, both suns would rise together. Other days, one would rise hours before the other. During certain seasons, the suns might chase each other across the sky, one setting as the other reaches its zenith. The shadows cast by this dual illumination would paint the landscape in patterns of extraordinary complexity, instead of the simple, sweeping shadows we know. Every object would cast dual shadows that separate and merge, creating what astronomers poetically describe as shadow play, geometric patterns that shift, not just with the time of day, but with the orbital positions of both stars in their celestial dance. As we contemplate this new orbital reality, we begin to realize that the very concepts of day and night, season and year, would need to be completely reimagined. But these changes in illumination are only the beginning. The complex heating patterns created by our planet's orbital dance with twin suns would reshape the very climate of our world, creating seasonal patterns unlike anything our single sun Earth has ever experienced. As our planet settles into its circumbinary dance, the very nature of light and shadow begins to transform in ways that would fundamentally reshape our experience of time itself. Picture yourself standing in a meadow during what we might call spring on this to-sun world, watching patterns of illumination that no human has ever witnessed, shadows that split and merge, seasons that layer upon seasons, and eclipses that paint this sky in choreographed darkness. In our familiar single-sun world, seasons follow a predictable rhythm tied to Earth's axial tilt and orbital position. But in a circumbinary system, seasonal patterns become a complex symphony with multiple movements playing simultaneously. Recent research published in the Journal of Geophysical Research has revealed that Earth-like planets in binary systems experience what scientists call nested seasonality, shorter seasonal cycles embedded within longer ones, creating climate patterns that shift on multiple time scales at once. The fundamental driver of these strange seasons lies in the orbital mechanics we've just explored. As our planet traces its circumbinary path, the combined radiation from both stars varies not just with our planet's distance from the binary center, but also with the stars' positions relative to each other and to us. When both stars align on the same side of their mutual orbit, our world receives what researchers term conjunction heating, a period of intense warmth that might last weeks or months, depending on the binary's orbital period. Imagine standing in that meadow as conjunction season approaches. The morning sky grows progressively brighter over several days, as both suns rise closer and closer together. At the peak of conjunction, they appear almost as a single, blazingly bright star, casting sharp, singular shadows and bathing the landscape in a golden intensity that makes high summer in our world seem mild by comparison. Plants evolved for this binary world would have developed extraordinary adaptations, perhaps leaves that can rapidly adjust their angle to avoid being scorched, or root systems that can quickly access deep groundwater during these thermal peaks. But conjunction seasons are balanced by what astronomers call opposition phases. When the two stars position themselves on opposite sides of their orbit relative to our planet, during these periods, we never see both stars simultaneously at their highest point in the sky. Instead, As one sun sets, the other rises, creating what researchers describe as extended twilight, days where the transition from light to darkness and back to light stretches across many hours, with the landscape bathed in a soft, complex illumination that shifts continuously in color and intensity. The eclipse patterns in such a system create some of the most spectacular celestial displays imaginable, unlike our familiar solar eclipses, which occur when our single moon passes between Earth and the Sun. A circumbinary world experiences multiple types of eclipse events. There are the binary eclipses, when one star passes in front of the other, as seen from our planet, creating periods of reduced but complex illumination. These events follow the orbital period of the binary stars themselves, which might range from a few days to several months. University research into eclipsing binary systems has revealed that these stellar eclipses create distinctive light curves, patterns of brightness variation that are as predictable as clockwork. From our planet's surface, we might witness a primary eclipse when the larger star passes behind the smaller one, causing a dramatic dimming that could last several hours. Then, half an orbital period later, we'd experience a secondary eclipse as this smaller star disappears behind its larger companion, creating a more subtle but still noticeable reduction in total illumination. But the real magic happens during what astronomers call triple eclipse events, rare alignments when both binary eclipses and traditional solar eclipses occur simultaneously. If our two-sun world possessed moons, these celestial bodies could occasionally align with both stars at once, creating eclipse patterns of breathtaking complexity. Picture a sky where one sun dims as it passes behind its stellar companion, while, simultaneously, a moon's shadow sweeps across the landscape, blocking the light of the second star. The dual shadows cast by twin suns would create a landscape unlike anything in our experience. Every tree, every building, every person would cast two distinct shadows that dance and merge throughout the day. Early morning might find these shadows stretching in nearly parallel lines. As both stars rise close together, by midday, depending on the binary's configuration, the shadows might point in completely different directions, creating crosshatched patterns of light and shade that shift and evolve with each passing minute. Research conducted using 3D climate modeling has shown that these complex lighting patterns would drive equally complex atmospheric dynamics. The varying angles and intensities of dual illumination would create temperature gradients that shift throughout the day and season, driving wind patterns and weather systems unlike anything on our single sun Earth. Convection currents might form and dissipate in rapid succession as different regions of the atmosphere receive varying amounts of radiation from different directions. The habitable zone around binary systems, that critical range of distances where liquid water can exist, presents its own fascinating complexity. Unlike the relatively stable habitable zone around single stars, binary systems create what researchers term dynamic habitable zones that expand and contract based on the combined luminosity output of both stars during conjunction phases. The habitable zone might extend much farther from the binary center during opposition phases. It could shrink significantly, creating temporary climate refugia where life might retreat during the most challenging thermal periods. Perhaps most remarkably, recent observations of real circumbinary planets have revealed that worlds in binary systems can maintain surprisingly stable average temperatures despite these dramatic variations in heating. The gravitational dynamics that keep planets in stable orbits around binary stars also create natural averaging effects in climate. The rapid changes in illumination tend to even out over time, creating what one researcher describes as thermal buffering. The planet's atmosphere and oceans act like enormous thermal masses, absorbing energy during peak heating phases and releasing it during cooler periods. As we stand in our imagined meadow, watching the interplay of dual shadows and feeling the complex warmth of twin suns on our skin, we begin to understand that this is not merely a brighter or dimmer version of our familiar world. This is a planet where the very rhythms of energy flow, of seasonal change, of the daily cycle of light and darkness, follow patterns that would reshape the fundamental processes of climate, and whether the atmosphere above us would dance with complex thermal currents. The oceans would pulse with tidal patterns influenced not just by moons, but by the gravitational variations of the binary system itself, and life, incredible and adaptable life, would find ways to thrive in this world of shifting illumination, evolving mechanisms we can barely imagine to take advantage of the rich complexity of a two-sun world. The atmosphere above our two-sun world would dance with thermal currents, unlike anything in Earth's experience, creating weather patterns that pulse and shift with the complex rhythms of binary illumination. As we drift deeper into this cosmic thought experiment, imagine standing on a beach where gentle waves lap against shores warmed by the intricate interplay of stellar radiation, while overhead clouds form and dissipate in patterns that follow not just the familiar cycle of day and night, but the far more complex orbital dance of twin suns. Recent research published in Nature Communications has revealed fascinating insights about climate dynamics on circumbinary planets. Through the first three-dimensional numerical experiments of water-rich worlds orbiting double stars, these groundbreaking studies show that the periodic forcing of the atmosphere by dual stellar radiation has a profound and measurable impact on planetary climate, with signatures of the binary system's orbital frequencies appearing throughout the atmospheric circulation patterns. The fundamental driver of weather in our two-sun world would be the constantly shifting thermal gradients created by variable stellar heating. Unlike Earth's relatively stable solar input, a circumbinary planet experiences what climate scientists call periodic insolation forcing, dramatic variations in the amount and distribution of energy reaching different parts of the planet's surface during conjunction phases, when both stars align to deliver maximum combined radiation. The temperature gradients between polar and equatorial regions would intensify rapidly, driving powerful atmospheric circulation patterns. Picture the morning after a conjunction peak, when both suns have risen together and bathed the landscape in their combined radiance. The differential heating between land and ocean would be far more extreme than anything we experience on Earth over large continental masses. The air would heat rapidly and begin to rise in powerful convection columns, their tops reaching into the stratosphere and spawning cloud formations of extraordinary complexity. Meanwhile, the oceans, with their greater thermal mass, would absorb and store this excess energy, creating temperature differences that drive wind patterns across vast scales. The ocean currents in our binary world would follow patterns of mesmerizing complexity. On Earth, our ocean circulation is driven primarily by solar heating, the planet's rotation, and seasonal temperature variations. But research from the Journal of Geophysical Research shows that circumbinary planets experience what oceanographers might call multi-frequency thermal forcing. The oceans respond not just to the planet's own seasonal cycle, but to the orbital period of the binary stars themselves, creating layered circulation patterns that operate on multiple timescales simultaneously. Imagine standing on a cliff overlooking one of these alien oceans during an opposition phase. When the two stars are positioned on opposite sides of their orbit, the sea below might be experiencing what scientists term differential tidal heating. One hemisphere, air warming under the light of the primary star, while the other cools under the dimmer radiation of the secondary. This would drive thermohaline circulation patterns far more complex than Earth's great conveyor belt of ocean currents, with warm and cold water masses moving in intricate three-dimensional spirals that redistribute heat across the planet's surface. The atmospheric dynamics would be equally fascinating. Climate modeling studies using 3D atmospheric simulations have shown that binary planets can maintain surprisingly stable average temperatures, despite extreme variations in heating. The key lies in what researchers call atmospheric thermal buffering. The rapid circulation of air masses helps average out the temperature extremes, preventing runaway heating during conjunction phases and moderating cooling during opposition periods. During peak conjunction seasons, when both stars deliver maximum energy, the atmosphere would respond with what meteorologists might describe as enhanced convection cycles. Towering cumulus clouds would form more rapidly and reach greater heights. Driven by the intense surface heating, these clouds would then spread into vast anvil formations, creating natural shade that helps regulate surface temperatures. The increased evaporation from oceans and lakes would load the atmosphere with water vapor, leading to more frequent and intense precipitation events that help transport excess heat away from the surface through the energy released during condensation. But, perhaps most remarkably, recent studies have revealed that circumbinary planets exhibit what climate scientists call resonant atmospheric patterns, circulation features that lock into phase with the binary orbital period. These patterns create predictable weather cycles that repeat not just seasonally, but in harmony with the dance of the twin stars. A farmer on such a world might learn to plant crops, not just according to the planet's seasonal cycle, but according to the longer rhythm of binary conjunction and opposition. The jet streams in our two-sun atmosphere would trace paths of incredible complexity across the sky, unlike Earth's relatively stable jet stream patterns, driven by consistent solar heating and the planet's rotation. A binary world would experience jet streams that meander and shift in response to the changing thermal gradients created by dual stellar heating. During certain phases of the binary cycle, multiple jet streams might form at different latitudes, creating a braided pattern of high-altitude winds that would influence weather patterns across entire continents. Ice ages and warm periods would follow cycles far more complex than Earth's Milankovitch cycles. Research on binary system climatology has revealed that planets in such environments can experience what glaciologists term nested ice age cycles, longer-term climate shifts, driven by gradual changes in the binary star's orbital parameters, overlaid with shorter-term variations tied to the binary orbital period itself. A planet might experience multiple mini-ice ages and warming periods within a single binary orbital cycle, creating geological records of extraordinary complexity. The polar regions of our binary world would be particularly fascinating. During certain configurations of the binary system, the poles might receive almost continuous illumination as one star sets and the other rises, preventing the formation of permanent ice caps. During other phases, both poles might be plunged into extended darkness, allowing ice sheets to advance rapidly toward lower latitudes. The aurora displays in these polar regions would be spectacular beyond imagination as the planet's magnetosphere interacts with the varying stellar winds from both stars, creating light shows that shift in color and intensity with the binary orbital cycle. As we contemplate this world of complex weather patterns and shifting thermal gradients, we begin to understand that life itself would need to be extraordinarily adaptable to thrive in such an environment. The plants and animals that evolved under these twin suns would have developed mechanisms for surviving rapid climate shifts, seasonal variations that operate on multiple timescales, and weather patterns that pulse with cosmic rhythms. They would be life forms shaped not just by the steady hand of evolution, but by the dynamic choreography of binary starlight. If humans had evolved in a world illuminated by twin suns, our very understanding of time, space, and consciousness would be fundamentally different from anything we know today. Picture a child born under binary starlight, growing up in a world where shadows dance in pairs, where the concept of noon requires specifying which sun has reached its zenith, and where the rhythms of daily life pulse to the complex heartbeat of orbital mechanics rather than the simple turning of a single world. The human circadian system, that ancient biological clock that coordinates our sleep, wakefulness, and countless physiological processes, would have evolved along entirely different pathways. Current research reveals that our circadian rhythms are regulated by the suprachiasmatic nuclei in the brain, a master clock composed of thousands of genes that switch on and off in specific orders, all synchronized to Earth's 24-hour rotation. But in a binary star system, human biology would have needed to develop what chronobiologists might call hierarchical circadian architecture, multiple interlocking biological clocks, operating simultaneously. Imagine the sleep patterns that might emerge in such a world. During conjunction phases, when both suns illuminate the sky with intense, combined radiance, humans might have evolved to embrace what researchers call polyphasic sleep cycles, multiple shorter rest periods distributed throughout the day to avoid the peak thermal stress of dual stellar heating. But during opposition phases, when extended twilight periods create gentler, more complex lighting, our binary-evolved ancestors might have developed the capacity for longer, more consolidated sleep periods, taking advantage of the cooler, more comfortable conditions. The research shows us that light color acts as an essential regulator of biological timing. Blue light suppresses melatonin production 5 times more than orange-yellow light, and different spectral compositions dramatically affect our internal clocks. In our two-sun world, humans would have evolved to respond to the complex spectral mixing that occurs as different stellar types interact. Perhaps we would have developed the ability to produce different neurotransmitters in response to different combinations of stellar light, one hormonal response to the warm yellow of the primary star alone, another to the cooler red of the secondary, and entirely different biochemical cascades during the spectacular moments when both stars share the sky. The architecture and urban planning of human civilization in this world would be marvels of engineering adapted to dual illumination, unlike our Earth cities. Designed around the predictable path of a single sun, binary world settlements would need to account for constantly shifting shadow patterns and multiple optimal orientations throughout the day and binary cycle. Buildings might be constructed with rotating facades or adjustable wall systems that could optimize for different stellar configurations. Picture walking through a city square designed for two suns. The central plaza might feature a magnificent sundial with dual gnomons, creating shadow patterns so complex they would serve not just as timepieces, but as works of art that transform throughout the binary orbital period. Public spaces would be designed with multiple gathering areas, some optimized for single sun illumination, others perfect for the intense but brief moments of conjunction, and still others designed as retreats during the peak heating phases when both stars align their energy toward the planet. The development of timekeeping and calendar systems would reflect the extraordinary complexity of binary illumination patterns. Unlike our Earth calendars based on single solar cycles and lunar phases, a binary world civilization would need to track multiple overlapping rhythms simultaneously. They might develop what chronologists could call nested calendar systems, daily cycles embedded within binary orbital periods, which would themselves be nested within the longer seasonal cycles of the planet's own orbit. Around the binary center, imagine the beautiful complexity of their temporal vocabulary. They might have dozens of words for different types of dawn: the first light dawn, when only one star rises; the harmony dawn, when both stars appear together; the chasing dawn, when one sun rises as its companion sets. Their mythology would be rich with stories of the stellar siblings, tales that would help children understand the cosmic choreography that governs their daily lives. The cultural implications would extend far beyond practical considerations. Art forms would emerge that simply cannot exist in our single-sun world. Painters might specialize in capturing the unique color combinations that occur only during specific binary configurations, perhaps creating works that change appearances viewing light shifts from one stellar type to another. Sculptors would design pieces that create different shadow patterns depending on the stellar configuration, works of art that transform throughout the day and binary cycle. Music, too, would reflect the rhythmic complexity of binary existence. Composers might create symphonies structured around binary orbital periods, with movements timed to coincide with conjunction and opposition phases. Perhaps they would develop musical scales based on the frequency ratios of the binary orbital period, cosmic harmonies that reflect the gravitational music of their twin suns. The spiritual and philosophical traditions of binary world humans would grapple with concepts of duality, balance, and cosmic harmony in ways our single-sun spirituality cannot fully comprehend. Their creation myths might tell stories of twin, cosmic forces that must work together to create and sustain life, rather than our often singular divine concepts. Their understanding of time would be inherently more complex, more nuanced, and perhaps more aligned with the actual rhythms of cosmic existence. Educational systems would need to prepare children for lives governed by multiple, interconnected cycles. Young students would learn not just basic arithmetic, but the complex calculations needed to predict optimal planting times, travel conditions, and social gatherings based on binary stellar positions. They would grow up with an intuitive understanding of orbital mechanics that would make them natural astronomers and navigators. Perhaps most remarkably, the pace of life itself would be different. Unlike our Earth urgency driven by single solar days and annual cycles, binary world humans might have developed a more patient, rhythmic approach to existence. They would understand, at a cellular level, that some activities are best undertaken during certain stellar configurations. That patience and timing are more important than simple speed, and that the most beautiful and productive moments often require waiting for the perfect alignment of cosmic conditions. As we imagine these binary world humans looking up at their twin suns, we realize they would see not just sources of light and heat, but partners in a cosmic dance that shapes every aspect of their existence. Their relationship with the heavens would be more intimate, more complex, and perhaps more wise than our own single-star perspective. But even as we marvel at how such a civilization might flourish, we must remember that all stars, including binary companions, follow the great cycles of stellar evolution. Eventually, even the most stable binary systems face changes that would challenge any world caught in their gravitational embrace. In the gentle valleys and rolling hills of our two-sun world, life would have learned to dance with light in ways that stretch our understanding of adaptation itself. Picture walking through a forest where every leaf, every flower, every creature has evolved not just to survive, but to thrive under the complex rhythms of binary illumination. Here, evolution would have been shaped not by the steady heartbeat of a single sun, but by the intricate symphony of dual stellar companions, creating life forms of extraordinary beauty and resilience. The foundation of all complex life. Photosynthesis would have evolved along pathways that seem almost magical to our single-sun experience. Research published in the journal Astrobiology has revealed that Earth-like planets in binary star systems could support what scientists call exotic photosynthesis, including organisms specialized for infrared radiation and creatures adapted to rapidly shifting spectral environments. These studies modeling photosynthetically active radiation levels in various binary configurations, show that familiar plant life could coexist with entirely new forms of photosynthetic organisms. Imagine plants that have evolved dual photosynthetic pathways, one optimized for the warm, yellow light of the primary star, another for the cooler, redder radiation of its smaller companion during conjunction phases. When both stars illuminate the landscape together, these remarkable organisms would activate both systems simultaneously, achieving photosynthetic efficiency rates impossible under single-star illumination. Their leaves might shimmer with an iridescent quality, containing specialized chloroplasts arranged in layers to capture different wavelengths from different stellar sources. But perhaps even more fascinating would be the plants adapted for the opposition phases of the binary cycle, as one star sets and its companion rises, creating those extended twilight periods we explored earlier. Entire ecosystems would have evolved to take advantage of this unique lighting. Picture ferns with leaves that can rapidly reorient themselves as the dominant light source shifts across the sky, or flowering plants that bloom exclusively during the brief moments when both stars share the horizon, their petals designed to attract pollinators active only during these rare, perfectly balanced illumination events. The challenge of variable light cycles would have driven the evolution of what biologists might call multi-frequency circadian systems. On Earth, most organisms follow circadian rhythms synchronized to our planet's 24-hour rotation. Circadian rhythms are natural oscillations that repeat roughly every 24 hours, regulated by biological clocks that coordinate biological processes to maximize fitness. But in a binary system, life would need to respond not just to the planet's day-night cycle, but to the longer rhythms of the binary orbital period. Recent research in chronobiology has shown that circadian rhythms have evolved to help organisms anticipate changes in radiation, temperature, and food availability. In our two-sun world, organisms would have developed what we might call nested biological clocks, shorter rhythms, governing daily activity cycles, embedded within longer rhythms that respond to conjunction and opposition phases. Birds might migrate not just seasonally, but following the binary cycle, timing their journeys to coincide with optimal conjunction heating phases, when food sources would be most abundant. The sleep patterns of animals in this world would be wonderfully complex. The daily light-dark cycle governs rhythmic changes in behavior and physiology of most species, with light and dark having the biggest influence on circadian rhythms. But imagine nocturnal creatures that remain active during single-sun nights, but rest during the deeper darkness of binary opposition nights, when both stars are below the horizon simultaneously. Or consider animals that have evolved polyphasic sleep patterns, taking advantage of the complex illumination cycles to remain active during multiple dawn and dusk periods within a single day. The evolutionary pressure to adapt to variable radiation levels would have produced remarkable physiological innovations. Plants might have evolved dynamic protective mechanisms, leaves that can rapidly change color or orientation to prevent damage during intense conjunction phases, or root systems that can quickly tap deep groundwater reserves during thermal peaks. Some species might have developed what ecologists call phenotypic plasticity, the ability to dramatically alter their appearance and behavior within a single lifetime. Based on the binary system's current phase, migration patterns would follow. Routes and timings unlike anything on Earth. Imagine vast flocks of birds that migrate not north and south with the seasons, but in complex patterns that follow the optimal heating zones as they shift across the planet's surface during binary orbital cycles. These creatures would possess internal navigation systems calibrated not just to magnetic fields and star positions, but to the subtle gravitational variations created by the binary system's changing configuration. The deep ocean life in our two-sun world would be equally remarkable, while surface organisms adapt to variable illumination. Deep-sea creatures would evolve to take advantage of the complex thermal currents and nutrient upwelling patterns driven by binary heating. Bioluminescent organisms might have evolved multiple light-producing systems, each synchronized to different phases of the binary cycle, creating underwater light displays that pulse in harmony with the orbital dance of the twin stars above. Perhaps most intriguingly, research into exotic photosynthesis suggests that binary star systems could support organisms that utilize forms of light invisible to our Earth-adapted eyes. Studies modeling binary star systems with M and G star combinations found environments that allow for infrared photosynthesis and organisms specialized for specific radiation environments. Picture walking through meadows filled with plants that appear almost translucent to our vision, but are brilliantly colored in the infrared spectrum. Their surfaces alive with patterns and hues that only creatures evolved under binary starlight could perceive. The pollination networks in these ecosystems would be marvels of temporal coordination. Flowers might bloom in carefully timed sequences that follow not just daily cycles, but the longer rhythms of binary illumination. Some plants might flower only during rare triple conjunction events, when both stars and perhaps a moon align to create perfect lighting conditions. The pollinators for such plants would be equally specialized, perhaps emerging from dormancy only during these astronomical alignments. Their life cycles synchronized to cosmic clockwork, spanning years or decades. As we walk through this imagined forest, listening to bird songs that follow binary rhythms and watching light dance through leaves evolved for dual star illumination, we begin to understand that life itself would be fundamentally different in such a world, not just adapted to different conditions, but operating according to entirely different principles that embrace complexity rather than simplicity, change rather than stability, and the beautiful challenge of thriving in a universe where every dawn brings new possibilities. But perhaps the most remarkable evolution in such a world would be the development of consciousness itself. For if intelligence eventually emerged among creatures adapted to the rhythms of twin stars, their entire understanding of time, pattern, and cosmic order would be shaped by experiences no human has ever known. Scientists just discovered that having one sun makes Earth the cosmic weirdo. Over 60% of star systems have multiple suns, and the life that could evolve there would make humans look primitive. Imagine waking up tomorrow to two suns in your sky. Your sleep schedule would be destroyed. Your plants would die. and your entire understanding of time itself would become meaningless overnight.